Alright, this is part 2 of our lesson on graphing rational functions and analyzing them. I like to start with the vertical asymptote, and we're going to get that by setting the denominator equal to 0, because we know that the denominator can't equal 0. That's why there's an asymptote. So we will just add 3 to both sides. So that gives us x equals 3. So that will be the vertical asymptote, x equals 3. And there it is. Alright, now let's talk horizontal asymptote or slant asymptote. It can't be both. Can't be both. So let's look at the rules. So remember, the horizontal asymptote is the one that's all about the degree of the numerator as opposed to the degree of the denominator. So which one of these situations are we in? Is the degree of the numerator less? Is the degree of the numerator equal to? Or is the degree of the numerator greater than the denominator? Okay, so the degree of the numerator is 2. The degree of the denominator is 1. So the numerator has a higher degree. Now, if the degree of the numerator is greater, that means there will be no horizontal asymptote. Now, maybe there's a slant asymptote. That's what this yellow part is. If it happens that the degree of the numerator is 1 greater than the denominator, then there will be a slant asymptote that will be like y equals mx plus b. And we will get that slant asymptote by doing long division, ignoring the remainder. So yes, the degree is 1 higher than the denominator. So there will be no horizontal asymptote, so we can just put none. But there should be a slant asymptote, which we will find right now by doing long division. So we will do x minus 3 divided into x squared minus x minus 2. Okay, so x times x would give me x squared. Alright, meanwhile x times negative 3 is negative 3x. Now we subtract by changing the signs. So that's going to give me 2x. And I will bring down the minus 2. Now, x times 2 will give me 2x. X times 2 is 2x. I want those to match. Now, 2 times negative 3 is negative 6. And I will subtract by changing the signs. So that is going to give me 4. Okay, but anyway, the x plus 2 that's up here at the top, that is the slant asymptote. Alright, we'll just disregard the remainder. We get the slant asymptote from the x plus 2. Okay, so that's why the slant asymptote will be y equals x plus 2. Alright, so that's like y equals mx plus b. This is the slope is 1 over 1, and the y-intercept is 2. Okay, so to draw that slant asymptote, you start off at the y-intercept of 2, and then you do your slope, that's up 1 over 1. So that up 1 over 1, it'll be like this, up 1 over 1, like this. Okay, and you continue the pattern in the other direction, down 1, left 1, all the way to the edge of the graph. So there is your slant asymptote. Okay, now will there be any holes? Well, holes happen when factors cancel out. Is this factorable? Well, you know what? Even if it is factorable, there's not going to be a factor of x minus 3. So there's no way x minus 3 is going to cancel out. So there won't be any holes. So we can just go ahead and put none. Okay, because holes happen when you have like x plus 1 times x minus 3 over, that's a 3, over x minus 3. When you have a factor that cancels out, then that would give me a hole at x equals 3. But that didn't happen on this problem. Even if this factors, it won't cancel out, so I'm not going to worry about it. So no holes. Alright, it's time to make our table of values. As you make your table of values, keep an eye on your vertical asymptote. We want to be sure we get values on both sides of the vertical asymptote, and so keep your eye on that. So my vertical asymptote's at 3, so let's definitely see what's going on at, let's say, 2, alright, as I go to the left. And I'm going to look at 1. I'm going to get all of these for sure. What's going on at 2 and 1 and 0, those would be good to know. Okay, and then I'm going to take a look at what's going on the other side. So what's going on at 4 and 5 and 6. Alright, so let's see what it looks like from these values, and if we need more we can always go back. Okay, so basically, okay, I just went ahead and put them in order. Alright, so let's use our calculator to help us out, because we will be allowed to do that. So we'll just type this into the table function to help us out. Alright, so it's x squared minus x minus 2. Over x minus 3. Okay, we're starting off at 0, so let's go ahead and tell it start at 0. Alright, so at 0 we're at 2/3. Alright, and then we have 1 and 0. And then next we have to skip down to 4, you know, because there's an asymptote there. So we have 4, 9, we have 10, 9, and 28 over 3 doesn't mean a lot to me, so let's go ahead and toggle it and see that it's 9.3. Alright, so this should be plenty to get us started. Okay, so 0, we're at 2/3. It's 2/3 of a square up, so that'll be about there. 1 comma 1, 2 comma 0. Okay, that gives us a good idea. And then we have 4 comma 10 is up there. 5 comma 9. Alright, 5 comma 9. And 6 comma 9.3. So 6, 9.3. Alright, and those are just enough points to give me an idea of what's going on here. If I need more points, I can just plot them. You know, I've got an unlimited supply of points that I can plot, so don't be stingy with your points. But I think this is enough for us to see what's happening. Now I might extend my line here because I can see it's sort of going to go off the graph a little bit. So I'm just going to stretch that out. And maybe I'll just, visually stretch this out as well. My slant asymptote is clearly doing this type of thing. Alright, so let's just draw our curves following the asymptote from there. Alright, so your graph should be looking like this. Alright, now we can answer some more questions. So the domain. The domain is the x value, so we can see it goes left and right forever, but it skips over the vertical asymptote. So it's going to be negative infinity to 3, and then 3 to infinity. And of course we will leave the 3 around parentheses to show that we are not including the 3. It's the asymptote. It can't be touched. Can't touch this. Do 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 do. Can't touch this. Okay, so the range. The range is the y values, and we're skipping more than just one y value. Look at this entire gap we have in here. Alright, all the y values between here and here. All these y values are being skipped. Okay, there are no, the function does not exist between these y values. Alright, so when we do the range, we have to do it from bottom to top. So the graph is coming up from the bottom, so that's going to be negative infinity to 1. Alright, that top value is there at 1. So negative infinity to 1, and then it's going to jump up here and go from 9 to infinity. Alright, bottom to top. So negative infinity to 1. Now this time we're going to put a bracket on it. It's not an asymptote or anything. It touches 1. It hits it. So it's included. So negative infinity to 1, and then it jumps up and goes, it picks up at 9 and goes from 9 to infinity. Now I said that I didn't actually do some sort of absolute analysis to see that 9 is the absolute local minimum here, and I didn't do the proper analysis to figure out that 1 is the absolute maximum. So I'm estimating, but for these purposes right now that's going to be good enough, unless we're allowed to use a graphing calculator. In fact, maybe I will go ahead and do the graphing calculator just to see how close we are. Alright, so graphing calculator. We'll go to that y equals, and again let's type this thing in. So x squared minus x minus 2 in the numerator. Let's see, I have to hit alpha y equals to go into fraction mode. So x squared minus x minus 2. So x squared minus x minus 2, and then x minus 3 in the denominator. So x minus 3. Alright, let's take a look at the graph and see what we have. Alright, so there's a graph looking very much like we anticipated. Okay, now let's see if we can find this local max and this local min. Alright, first of all, this local max right here. So if I do second trace and I want to find a maximum, so I can choose option 4. Now I estimate that the maximum is right about here. I need to pick a point to the left and to the right of it. So I see the cursor, I'm on the left, so I can just hit enter. Now it says what about to the right, so I can just scoot on over to the right of where I think it is and hit enter. and then I can just hit enter again. So the maximum is about at 1, comma 1, y value of 1. So that is what we thought. So we got lucky and actually nailed it. Now let's see if we'll be as lucky on the local minimum over here. Okay, so I'll do second trace again, but this time I want the local minimum, so I'll choose option 3. Now I'm on the wrong branch, so I need to hit the up arrow to get to the other function. Oh, you know what? I have to, never mind, it's not the up arrow. I need to go to the right until I get over there. Okay, there it is. You know what? I think it would help me if I change the window as well. I need to see more up top, so hit the window. I need to raise the ceiling, so that's the Y maximum. Alright, let's make that 20 and graph it. Okay, that I can see that a lot better. So I'm looking for this. So again, second trace minimum this time. So I'm just going to right arrow until I get over there. And there I am. So it's asking me for the left bound. So I see that the minimum is about here. So I want to make sure I stay to the left of it, and I hit enter. Then it's asking for a right bound, so I'm going to scoot over to the right of it. Okay, and hit enter. Then when it says guess, I'm just going to hit enter again. Okay, so the minimum seems to be at 5, 9. So it actually was what it appeared to be, which doesn't always work out that way, but that actually is the local minimum, so that's nice. Alright, now I can sleep at night knowing that I'm not actually just estimating. Okay, let's see, did they even ask us for the local max and min this time? They didn't even ask us for it. How about that? Anyway, the x-intercept and the y-intercept. In general, you will find the x-intercept when you let y be 0. Now, in terms of rational functions, sometimes it's easier to think of it as letting the numerator equal 0. Okay, so in general I say let y equal 0, but for rational functions that almost always comes out to be the same thing as letting the numerator equal 0. Alright, and I find the y-intercept by letting x equal 0. So first of all, let's find the x-intercept by setting the numerator equal to 0. Oh, I went too far. Okay, so if I set the numerator equal to 0, I have this. Maybe this is factorable. So let's try that. If it doesn't factor, I'll have to do the quadratic formula. X squared, that's x times x. 2 is 2 times 1. Inner plus outer has to equal middle. Inner I have 2x. Outer I have 1x. I can get a middle of negative 1 if I have a negative 2 and a positive 1. So that would be negative 2 and positive 1. And that does give me negative 2 because negative times a positive is a negative. So there I factored it. Now to find the solutions to this, I set these equal to 0. Okay, so let's just do it mentally. So that's going to give us x equals 2. If I set this equal to 0, well, this already has it. And x equals negative 1. So these are my x-intercepts, 2 and negative 1. So one of those we already had graphed, so we see it at 2. But also, here's the one that's at negative 1 as well. In fact, I probably should have found those before I drew the curve, just to help me out. Okay, so 2 and negative 1. So that's negative 1 comma 0 and 2 comma 0. Now the y-intercept. The y-intercept is where the x equals 0. So you see x was 0. We had a y value of 2/3. So this is the y-intercept right there, 0 comma 2/3. Okay, now how about increasing and decreasing intervals? Alright, so looking at this graph, it is increasing. So as I go along this graph, it is increasing. It's a little too much. It is increasing from here to here, increasing, increasing, increasing. Okay, that was all increasing. And then it switches to decreasing for a while. Okay, and then now it's decreasing. Okay. Alright, maybe I'll do this in green. That's what I usually do. Okay, so it's increasing up to here, and then it starts going downhill again. Now looking at this part over here, it sort of picks up from here. And so then it's decreasing for this part of the journey again, down to there. And then it's increasing from here to here. Alright, so the parts that I just highlighted in green are increasing. The parts highlighted in pink are decreasing. Now, we are going to be talking in terms of x values. So really focus on that. So right here, of course, the x value is 1. Right here, the x value is 5. So those are important points. Okay? Now, the other end of this, this is infinity over here, but what kind of infinity? We want x value, so don't worry about the fact that it's going down. It's going to the left. So this is an x value of negative infinity over here. Okay? Now, over here on the right of this pink area, this is not actually an infinity. Okay, even though I'm putting this arrow here, but the x value is approaching the asymptote, which is at 3. So this is going to count as 3. Alright, because it's going to just keep getting closer to that asymptote. And then over here, on this side, same thing. This is approaching the asymptote, so this is 3. Meanwhile, this end over here is just going to the right forever. So the x value of this is positive infinity. Not because it's going up, but because it's going to the right. So these are all x values. That's why this is not infinity. If you were thinking infinity, because look, it goes up forever. That's y values when you say up. As far as how far to the left does it go? It only goes as far as the asymptote, which is at 3. So these blue numbers are what we will use to describe what's happening. So our first increasing interval is from negative infinity to 1. X values only, please. So we'll say negative infinity to 1. And these always get round parentheses, never brackets. Alright, because right at the changeover, it goes from increasing to decreasing. But right at the number in the middle, it's neither increasing nor decreasing. It's flat for one moment. Alright, so then we have another increasing interval from 5 to infinity. So union 5 to infinity. And then decreasing intervals. Okay, we have a decreasing interval from 1 to 3. Got to stick to the x value, so 1 to 3. Union. Okay, and then we have another decreasing interval from 3 to 5. Okay, so that's 24 minutes that we spent talking about just one problem. But I feel it was well worth it. But I'm definitely going to stop this video now because it's over long and it was only one problem. I'll see you on the next video. On the next video, we'll pick up with number 3. Alright, where we're still kind of doing the same thing. Hopefully I can do it faster next time.